Well, hello there and welcome back for more Advent of Code. So today we are continuing where we left off last time. That will be day 9, and look at that, there is some golden percentage symbols here in the ASCII drawing. I wonder what that is about. Well, day 9 is called rope bridge, so maybe that was that was it. Maybe those characters represented the rope bridge. So let's read today's puzzle. Oh, it seems it's another grid-based thing. So okay, let's see. This rope bridge creaks as you walk along it. You aren't sure how well it is or whether it can even support your weight. It seems to support the elves just fine, though. The bridge spans a gorge which was carved out by the massive river far below you. Okay, so scary situation there. You step carefully. As you do, the rope stretches and twists. You decide to distract yourself by modeling rope physics. Maybe you can even figure out where not to step. Okay, maybe we're figuring out where not to step in this bridge. Consider a rope with a knot at each end. These knots mark the head and the tail of the rope. If the head moves far enough away from the tail is pulled towards the head. Okay, makes sense. Due to nebulous reasoning involving plank lengths, so it links to the Wikipedia article on plank length. Seems that we are dealing with quantum level stuff here. So, due to nebulous reasoning involving plank lengths, you should be able to model the positions of the knots on a two-dimensional grid. Yay, nice. Then, by following a hypothetical series of motions, your puzzle input, for the head, you can determine how the tail will move. Okay. Due to the aforementioned plank lengths, the rope must be quite short. In fact, the head and the tail, H and T, must always be touching, diagonally adjacent, and even overlapping both count as touching. Okay, so we can have them side by side or even diagonally touching, like at one distance away, or overlapping. Okay. If the head is ever 2 steps directly up, down, left, or right from the tail must also move 1 step in that direction so it remains close enough. Okay, so if the head moves like this, then the tail follows. Okay, fair enough. Otherwise, if the head and tail aren't touching and aren't in the same row or column, the tail always moves 1 step diagonally to keep up. Okay, this is nice. So here the head was diagonally touching, then moved up, and as it did so, the tail follows diagonally up and to the right. Good. You just need to work out where the tail goes as the head follows a series of motions. Assume the head and the tail both start at the same position, overlapping. For example, well, this I think would be the input. This series of motions moves the head right 4 steps, then up 4 steps, then left 3 steps, and so on. After each step, you will need to update the positions of the head of the tail if the step means the head is no longer adjacent to the tail. Okay. Visually, these motions occur as follows. S marks the starting position as a reference point. Okay, so they start here at 0, 0, let's say. Then we have R4, which means move to the right 4 times. So this is the first movement. The tail is still touching, so it doesn't need to move. Then it follows along, Okay, so it is 1, 2, 3, 4 steps. Okay. So when we see like R4, it's not like the head moves 4 immediately and then the tail follows up. It's just motions of one at a time. Okay. Then up 4, Okay, here we have that condition where the head moves to the top, but the tail remains there, diagonally touching, and then once the head moves up again, the tail follows. Okay, fine. And then we have all the motions here. We could even try to do these ASCII drawings, although I don't know if that will be necessary. Hopefully not. After simulating the rope, you can count up all of the positions that the tail visited at least once. Okay, in this diagram, S again marks the starting position, which the tail also visited, and hash, or I don't know how this is called, marks other positions the tail visited. Okay, so here we can see where the tail was moving around. So there are 13 positions the tail visited at least once. Simulate your complete hypothetical series of motions. How many positions does the tail of the rope visit at least once? Okay, this doesn't sound too complicated. And indeed, it kind of smells like it will be a very imperative solution, I think. Like, yeah, very imperative, total disregard for like functional purity. So let's take a look at the input. So it's a series of motions. They are all relatively small numbers here. Yeah, they're pretty small numbers. So I think we can do a pretty straightforward simulation. Like, we probably don't need to get clever and try to simulate, like, maybe if these motions were, I don't know, 1,000 or more long, we could try to figure out how to, you know, do it all at once, all the simulation at once. But I think given these small numbers, we can get away with just doing step-by-step simulations. So let's get to it. Go to Advent Code 2022, open up the code editor. We have day 8 here from last time. Oh, by the way, I found a way to avoid doing all the like type conversions between unsigned and signed integer types. What I ended up doing is using this wrapping add signed functions on unsigned integers, and so this basically takes care of the underflow condition, and it wraps around, so then I can only check the grid. Like, the out of bounds conditions become simpler too, and I don't have to like be converting to signed integers and then to unsigned integers again to access this grid. So that was a nice improvement there. But let's go to today's challenge. So it will be day 9 txt. It shall be the input, and let's copy the input, like the sample one, this one. Okay, and let's also create a new file for this challenge, day 9 rs. Let's import this in main and add it to the array of solutions. And here we're going to have a path function run that takes an input as a string slice and returns a new string. And what do we do? Okay, as usual, let's reload this file to have the editor know about the tab size. Okay, I think we can try to do a very straightforward solution for at least for part 1, and then see what part 2 is about. So I have no idea what it will be. So generally, I think we only need to like parse this input line by line and then simulate things step by step. So yeah, let's do that. So we're going to have, well, let's do the parsing first. So for each line in input lines, we're gonna do, well, we have to parse each of these lines. So they look like simple tuples. We can split by space here and get the direction that we want to move, and the number of steps that we need to do in that direction. So that would be, let's say, let's direction and step count be line split once, and let's split by a character. And this probably needs an expectation. Of course, we expect this to be line, we can say just invalid line. Let's keep it simple. And then we have to parse this step count as a number. So let's say that this step count is, I don't know, yeah, we can use just size. We don't need to index anything, so let's actually use, well, it doesn't matter here, right? It could be anything, but let's parse it into a 32-bit number. So step count parse, and again expect step count should be a valid number. Today I feel like using more shorter expectation messages. So this is a nice thing about Rust. You can shadow previously declared variables. So here we had a variable that was called step count, and it was a string. And you know, we could also have named this step count string or something, but we can have another variable named the same thing. And once I declare this, yeah, you can no longer see this first step count variable. This is a new variable that shadows the previous one, and I quite like it for these kind of things, kind of type conversion things and stuff like that. So now that we have this thing parsed, I guess we can iterate over, over these step count times. So let's say I don't think we need a name for this, in step count, and here we're going to simulate each step. Okay, so what are we going to do? We probably need to keep track of the head and tail positions. So let's say could use a tuple of xy coordinates, but let's keep it simple and say head x is 0, and let's make it mutable because we're going to need to update it. Okay, so let's first simulate all the head movements and print the results and see if we got it right, and then we can simulate the tail movements that follows the head. So what we're gonna do here is probably to match on this direction, and so I think these are just letters. RU, yes, right, left, up and down. So if it is left, we are going to do head x decrement by 1. If it is right, we're gonna do the same thing, but head x increment by 1, and then we can do same thing for up and down. So up and down, and we're going to do, well, head y, and here also head y. Here we're going to, or actually we can make the up be, yeah, we can make the up be positive. I think we don't need, usually in these diagrams, when you have a grid and you want to move up, you say that it's the negative direction, but I think in this case, even though it looks like, well, it is a 2D puzzle, I was thinking I probably don't need to even have a grid, like a 2D array or something to follow this. We can just keep track of the positions like this, and then remember where we have been. So we can make the up direction be positive and the down direction be negative. It doesn't like this, why not? Oh, no, not non-exhaustive pattern, of course. So anything else should be invalid. So let's say unreachable, and say invalid direction, and we can even include it here. Okay, so this is now updating the head, and I think that's all that we need to know about updating the head, right? So let's now print the final head position. It's gonna be head X and head Y. Okay, and let's run it. Cargo run day 9. Final head position 2-2. So does that coincide? Yes, indeed. This head seems to be at 2-2. So okay, that wasn't that difficult. It was pretty trivial actually. So now we need to do the same, but for the tail, like simulate how the tail moves. So let's do the same idea here. We're going to have a tail X be 0, and let's mutable tail Y be 0 also. So the starts up overlapping, and well, after the head has moved, then we will move the tail. So how are we going to do that? First, we have to figure out if the tail needs to move at all, because if it is close to the head, then it doesn't need to move. So we can do, we can take the difference of the head and the tail position. So let's say the X will be head X minus tail X, and same thing but for Y coordinates. So am I doing this in the correct order? Let's see if imagine that the head is at, I don't know, 1-1 and the tail is at 0-0. This thing will be 1-1, so it means that's the direction that we want the tail to move. Yes, it makes sense, and of course it can also be negative. So we can say, let's say that they are close, or that they are touching if the X oh, there's an absolute diff. That's that might be useful. What does it do? Come on, won't you show me the documentation for this? Let's go and see. Why don't you know about this? No definition, but you suggested this. What the hell? Ambiguous numeric type. You must specify a type for the binding. Okay. Sure. Let's do all of this be I32. Why not? Maybe this absolute diff is actually what we want here. The difference. Well, no, I think we actually need we need the sign, because we are then going to move in that sign. So we can actually do something like if dx, is there a sign? Sign num? Yes, this probably is what I want. Returns the number representing the sign. So it returns 0, 1, or -1. No, actually, I'm overcomplicating things. Let's do the absolute value of this and say, well, if the absolute value is less or equal to 1 for the x, and the dy absolute value is also less or equal to 1, then the head and the tail are touching, so we don't need to move the tail. Otherwise, we need to update it. So yes, if they are not touching, we're going to update the tail. So how are we going to update the tail? Well, we can do increment the tail position by this dx, but you know, if we just increment it right away, we are going to make them overlap. So we have to increment them at least by 1, I think. Yeah, I'm pretty sure. So we can do tail x at this dx, and here we can use the signum function. So this basically clamps the number to 1, 0, or -1. I guess we could also use the clamp. Yes, so maybe clamp here is more readable to what we want to do. So let's do that. And we will also update the tail position by the same idea. It moves at most once. And that's it, I think. I think that's how the tail should move. Now we need to remember where the tail has been, so let's also have a variable for that. We can use, I guess, a hash set, visited positions, a hash set. We could also use like a sorted array or something, or a sorted vector or something, but let's use a hash set of what? Well, we could use i32 tuples here. Okay, so this will be hash sets new. And I guess we could also, like if we add the position here at the end of the step simulation, then we're going to miss the first position of the tail. And if we add it before, then we are going to miss the last position. So let's add it. Let's add the first position, like the initial position, at the beginning. So let's say visit positions, inserts. I guess we could initialize it, right? Instead of saying new, we can say from receives a value. So I guess we could just pass 0, 0 as the beginning. Is this okay? Not really. So from receives from the input type. Is this what we want? So what's the problem here? Okay. From iter. Guess we could have an iterator for this, but dang it, let's just keep it as it was before. So just have a new thing and then insert the initial position. That will be 0, 0. I'm fine with that. And after the tail has moved, let's also insert the tail position. So that will be visited positions, insert the tail position, which will be tail x and tail y. And I think that's it. Let's print this thing, formats, and we're going to have the visited positions length. And let's see what this gives. 13. I think that was, yes, that was the answer for the sample input. So let's copy the actual input and see how it goes. You can save here and run again. 6,033 and 9. You can probably read that number correctly, but okay, that's a gold star. Very nice. This one was a pretty easy first part. Let's see if the second part, or the part 2, complicates things much. Okay, so part 2. The rope snaps. Oh no! Suddenly the river is getting a lot closer than you remember. The bridge is still there, but some of the ropes that broke are now whipping toward you as you fall through the air. So we are falling through the air and we're going to solve this puzzle. Okay, the ropes are moving too quickly to grab. You only have a few seconds to choose how to arch your body to avoid being hit. Fortunately, your simulation can be extended to support longer ropes. Rather than 2 knots, you now must simulate a rope consisting of 10 knots. 1 knot is still the head of the rope and moves according to the series of motions. Each knot further down the rope follows the knot in front of it using the same rules as before. Using the same series of motions as the above example, but with the knots marked H 1, 2, 3 up to 9, the motions now occur as follows. Okay, so I guess each rope knot is going to follow, like the head followed the tail, but now we have a lot of knots. So it's going to look maybe like I don't know how it's going to look. I don't know if it's going to look like a snake game or something different. So here H is covering everything. Then it updates and it goes to here. So far it makes sense. Then the head goes up. Oh, look at this. Here's the interesting bit, right? So the head moves up and yeah, the first knot follows in the diagonal motion, but all the other ones, like the second one also follows the first one in the diagonal way too. So this is the shape of the rope now, and then the head moves up, and oh, this is very interesting. Now the first knot follows, but the second one doesn't move because it's still at length 1. Very interesting. Then it moves this way, and then it's kind of whipping. It's actually doing kind of a rope motion. This is very nice that these simple rules actually produce a sort of rope kind of motion. And the 6th knot hasn't moved away, and it won't move away in this grid, right? Because this grid is like very short, but in our grid it's probably going to be much longer. Now you need to keep the track of the positions of the new tail, 9 visits. In this example, the tail never moves, and so it only visits 1 position. However, be careful. More types of motion are possible than before, so you might want to visually compare your simulated rope to the one above. Okay, here's a larger example. Okay, so we have a larger example now. Wow, okay. These motions occur as follows. Individual steps are not shown. So here we have the initial position, then it moves right 5, and it does this as we expect, then up 8, and this is how it ends. Okay, then left 8, look at that shape. I was not expecting that. Ah, well, okay, so it was here, it moves to the left. It sort of makes some sense. Very good. Very, very interesting. Now the tail, 9, visits 36 positions, including S, at least once. Simulate your complete series of motions on a larger rope with 10 knots. How many positions does the tail of the rope visit at least once? Okay, so our simulation with only 1 head and 1 tail, hard-coated, like a hard-coated rope of 2 knots will not extend very well to this larger simulation, I'm afraid. So we can probably do something similar to this. So still, the head does move in a very similar fashion. Actually, like the head will be the same, but we can consider the tail of the rope. Well, no, the tail is the last the last knot. It's not like in functional programming terms, like head is the first element and the tail is all the rest. So I'm a bit confusing a little bit. I'm tempted to do something similar to that. But we sort of have to generalize this thing to be able to simulate a rope of length 10, right? Yes. So we could start by kind of maybe extracting this into a function. And yes, yes, I think I want to do just that. Let's do something like, well, yes, just extract all of this. Let's call this thing run rope simulation. And we're going to pass a length of the rope that we are going to simulate and the input. Okay. And this will return like a number visited or tail. Actually, let's just print this thing in here. So, okay, save, and let's, well, it doesn't suggest me because it can't infer the types, I guess. So let's say fun run rope simulation is going to take rope length. It's going to be, well, the length could be, I guess, a size. Let's use a U32 because we are using 32-bit numbers for stuff. And then the input, so input shall be same thing, a string, and we're just going to return the number of whoops, so I screwed up and overwrote my clipboard data. So let's copy this, let's redo all of that and now paste. Okay, and here we're going to return the visited positions length. Okay, so let's make this compile again and run. So we should get the same number, of course. And now it's time to generalize this. So actually the two answers will be this rope simulation with length 2 and the same thing with a rope of size 10. All right. So now we can probably do have all the positions. So okay, the visited positions is gonna be same thing. Like these two are going to remain. Then instead of doing this, I think we're going to need like a data structure for the rope. So let's say, what are we going to use? Can we use a static array? I'm not sure. Let's say an array of tuples of size rope length. Can we have that? And initialize this with zeros. I don't know if this is going to be possible. So rope length, non-constant value is constant. This would need to be a const. Let's see if we can have a const. Const rope length, not really. Dang it, let's see if this is possible, otherwise I will just use a vector. So Rust const parameter. Const generics, wow, okay. Can we have this into just make a non-constant function? Yeah, okay, let's bite the bullet and have a vector. All right, you win, Rust. You want to have everything, I don't know, be memory friendly. Like, I don't know why this is not, I guess we could pass a giant value here and blow up the stack. So let's make this a vector of, well, starting everything at position 0 and have the size of rope length. Would you be happy with this? No, why not? Oh, because this is U32. Okay, yes, let's have a U size. So we're going to use unsigned sized integer, like U size integers for things that are usually use U size, like the length of a vector, or in this case, the length of this set. So okay, we have this rope, and now we can get rid of these variables. We're going to do something very similar here. So in order to update the head, what are we going to do? So let's see, I guess we could do something like keep something very similar here. If we get like, can we get the head as rope 0? And this would be, no, but let's actually take a mutable reference to this. So this would be the head, and here we could say something like, hey, update the head first coordinates and the second coordinates. Not very pretty, but it works. Yes. And can we do something like destructuring here? So instead of changing these variables, let's try to keep those variable names, but we are going to destructure here into head X and head Y. Can we do that? These are mutable references to I32, so it does make sense. And we can probably dereference this. Yeah. Okay, cool. Very nice. So the head updates, I think we are done with that. Seems good to me. And then we want to update the rest of the positions, but like following the same logic as the tail did, but now each node will follow the next one. So how are we going to do that? We could do, so the head is the element on this rope on the first position, and the tail is the one at the last position. So maybe let's do another iterative loop here for I in yes, we could actually even use okay, so we are going to update one of these positions. So this mutable reference that we took here, we are done with that. We won't update it anymore, so Rust shouldn't complain about that. But I wonder if it will let us update things while reading something else. That's going to be challenging, maybe. So okay, let's first code this with indices, and then we can think about something more clever. So here we can use rope length, or the variable rope length would be the same thing. Yeah, so we are gonna, what are we going to do? We're basically going to do this same thing, but instead of having the head and the tail, we are going to have like the one knot that follows the other knot. So we can have let knot be the rope at this position I, and let's have the previous knot be the same thing as position I minus 1. So here the X is going to be so instead of head we have the previous knot, and well, this is the first coordinate and this is the second coordinate, and minus the knot first coordinates and then the second coordinates. Okay, so that should still be the same. Touching doesn't like this. Why not? Ambiguous numeric type. But why is this an ambiguous numeric type? You know that it is I32, don't you? Where do you want this type binding? So yeah, these arrows. Really? Do you need a type binding here? Like, these things are I32s. I'm not sure if that's an actual problem. Let's finish with this. So here we need to update this position. So this will be the knot X and the knot Y. First and second things, and then, well, we have local variables here. They are not mutable references, so we have to update this thing on the rope. So rope I is gonna be the updated knot, right? I think so. And visited positions here, instead of using the tail, we're going to insert the rope last element, which would be in rope length minus 1. Really, do you need this? Seems very weird, because here it can infer the type the type correctly. So, well, let's add the type annotations here. Why not? And we cannot update this because these are not mutable variables. Let's make it a mutable variable, because this is a clone, like a copy of this. So then we need to update this thing. Okay, so I don't know if I actually did this thing correctly. Let's run the simulation with initial input. So okay, only one visited position as was expected. then let's run it with the bigger input. Where is it? Here. To have an idea if we are doing things right. Now it's 36. So is this correct? Yes, 36 positions. So now let's try out the actual input. So in here, paste this, and run the simulation. And this number, let's try it out. Again, I keep alt-tabbing to the wrong thing. Submit. Yes, very nice. Okay, so this one wasn't too hard. So yeah, look at that. That really looks like a rope bridge. Very, very good. And now day 10, I don't know what this is about. So if I visit day 10, do I then have the... No, I don't see the drawing. So I don't know why I was seeing this drawing, but we are basically falling to our deaths. I don't know if we managed to survive here. Yes, okay. Very nice. We got this thing working, and we can call this thing run rope simulation, or sim for short. And I'm pretty happy with this initial solution. I don't know if I would change much. Maybe let's shuffle some of these things around. We have the rope and the visit positions. Yeah, we can probably do something like... I really want to have something that does this. So can we do like into iterator here and collect? Would you be happy with this? Yes, you are. So nice. And then I don't really like some of the stuff that we were doing here. It's not too bad either. So this is the tail. We can probably extract this into a variable. Let's call it tail. And yeah, I guess the only thing that I would change here would be to have here we are getting a mutable reference, but I think that would be a problem here. Like if we get a mutable reference to this thing, we are going to be screwing things up. Like getting a mutable reference here, but then getting... Oh, I guess we could copy this and not have a mutable reference. So I wonder if that would work. Let's see, let's add this for now. And now try to do this the same way that we did the head update. So let's see, let's not x and not y be a mutable reference to this thing. So here we're going to do not x and not y, and we are going to need some dereferencing, sure, and then we are going to the touching calculation is the same. We call it not touching, yes, and then we can update not x and not y directly, and we don't need to do this. I think Rust should be happy because, oh no, it isn't. We cannot borrow this immutably because we are also taking a mutable reference here. So yes, but maybe we can do it the other way around. So here we are making a copy of this, so that should be fine. And we can actually destructure here, so we can call this priv not, or yeah, priv not x and previous not y. So yeah, x and y. And sure enough, now Rust is happy. And does it give us the same answer? Yes, it does. So we are updating things directly by references here. I don't know if yeah, it seems more direct. Sure enough. Is there anything else we would like to do here? I'm not really sure. There is one thing maybe that I would like to try. Well, actually, here we are doing this thing that we have seen in some other puzzle before, where we are taking like two at a time, 2 elements at a time. And I think this can also be done with some other iterator called windows. Oh, what are array windows? I wonder. Oh, this is interesting. I wonder if we could use this. So let's, before trying anything else, let's also add this change. Let's see if that could be something useful. So we can use rope array windows of size 2. Actually, can you even infer that size if we say here we're going to have the previous not and the not that we want? Array windows. Oh, unstable library feature array windows. It's an unstable feature, this thing. Let's see if it has been released or anything. No, it's still an open, unstable feature. So, too bad, I think. Yeah, we don't need to use unstable Rust. I don't want to switch to Rust nightly or something like that. So going from 1 to till the end of the rope seems fine. Yes, and then we are updating this knot. And then we put the tail position into the... Yes, I think this code is pretty much good enough, I would say. Is there anything else that I could change on this? We are doing the parsing of this thing twice. I guess we could maybe do it once, but it's not really necessary. One thing that I would like to try, however, is to like kind of combine these two loops into one, because here basically all the interesting step simulation is done in this inner loop, and these two loops I guess could be combined. I think if we did something like if we did something like, let's see, here we are parsing this. Is there something like std iter, what do I want, like repeats? Yes, repeats. Oh, we create a new iterator that endlessly repeats a single element. Okay, I guess we could do this and then take take some amount, take some of those. Like we have an infinite iterator and then take, instead of doing this, I guess it's the same thing. Not much difference really. But yeah, if we do something like, let's try. I want to play around with iterators. So we can have something like, let moves be, or steps, let's say, step moves be input lines, and then we are going to flat map this, each line, into what? Well, let's move the parsing over here. We have the step count and we have the direction, so we're going to return this repeating iterator, and we're going to repeat the direction let's get the first character, I guess, or the first byte. Charles is also an iterator. Let's do direction be this direction. We cannot index into a string, but can we get the first? Just take, not take, next, I guess. Next, yes, and expect, not really. What do I want from here? We cannot index, but can we slice into, what would direction be in this case? A string slice. Huh. But still, then we don't need, I think we wouldn't be able to, we wouldn't be able to access the first element here. No, not really. So I just want one character, man. But well, we can make direction be a string and that's it. No need to worry about this. So let's repeat this direction n times. So take step count. So now this thing, why don't you like this? Why do you want these? What does repeat? No, we don't. I don't want that repeat. What did I import? Oh, IO repeat. I don't want that. I want the other repeats from std iter, I think. Yes. And step count. Sure, it should be a usize. Sure enough. Can we actually import this thing? Okay. And now we can like simplify these two nested loops into one and say for direction in step moves and remove this inner loop, we're going to simulate each step. Direction here, yes, it's a reference to string and everything should be just fine. It still give us the same answer. So I think we can even extract this thing into a function. So we can extract this into a function. So it's going to be something like parse moves. Okay. And now this is an error, right? Yeah. So here we are, yeah. We need to return something. So can you infer it, Rust? Come on. Can you give us the error? Or the expected type, I guess. If we put something invalid here. Sure, so these types for iterators are kind of a mess because the complete type, as you can see, is like a flat map iterator of a take and repeat and blah, blah, blah. And it also includes the specific type for disclosure and all of that. But I think I can use something like impl iterator. And this would be an iterator of type string, something like that. It's not that. Is it something like, yeah, item equals string? Okay. And now the type checker is happy. So we don't need to specify exactly like the specific type that this returns. There is going to be a specific type, but we don't need to spell it out completely. We can let Rust infer it and use it, and then use it here. So now we are having like a single unrolled or flattened loop for each of these directions, and I think it reads a bit better. First we are updating the head, and then we are updating each node. And then we are remembering which positions the tail visited. So yeah, I think that's a pretty good change. Let's see if it still runs. Yes, it does. So we are doing the parsing twice here because we are running the simulation twice, but I think it's not necessary to worry about this kind of performance minutia yet. If I really cared about that, I should profile the thing and see if it makes any difference to do the parsing only once. But for now, I think that's it. It was a pretty much simpler challenge today than it was yesterday's, or which one was it? Yeah, the one about the file system counting of directory sizes. That one was much more challenging, and I guess the puzzles do get progressively harder as time goes by, but I really like it that it's not always harder. So sometimes you get a simpler puzzle and it's kind of a breather. And if I would be following this day by day, which I'm not, this would have been a nice surprise to find a simpler challenge. So let's see if there's anything else that I would want to change here. I guess we could do some better modeling of this and call this thing a position type, and maybe extract this into like update head, and this into like this logic into like update not or something like that. But I think I am all right with what we have now. It's not too much code, and I still wonder, are these type annotations really necessary? Yes, they are. I don't understand why. So why does the abs function not know about about the type of this? If this, this is like a operation on two I32 values, why wouldn't it know about that? I don't know. It's weird to me. But anyway, this code is fine. Let's see the parsing code. We have the split once, invalid line, fine. And the parsing of a step count, that's also fine. And then we are repeating the direction this amount of times. Yeah, I think I'm happy with that. Yeah. Yeah, very well. This I don't know if this code is very trivial to follow, but it's like basically flattening this input into, instead of saying L10, it's going to be, 10 times the direction L for left. I could also, I guess, model this into an enum or something like that, but, no, not really necessary. So yeah, I'm happy with this. Let's commit. And day 9 solution. So okay, this one, I don't want to fall in the usual trap of trying to refactor this way too much. I think this is okay code as it is, and doesn't need any more improving, I think. So I want to say, if you have been watching, thanks for doing so, and see you next time. Bye bye.